We have studied the classical relativity. Then we have gone through Galilean transformation, and you have seen the Galilean transformation may be used to find the velocity transformation equations. And actually the velocity transformation equations obtained from the Galilean transformation was in fact insufficient to explain the fact that speed of light in free space is same in all inertial systems in relative motion with respect to one another. It means according to the classical velocity transformation equation, or you can say Galilean transformation for velocity, actually the result is found that the speed of light in free space will be different in different inertial frames. But according to the second postulate of spatial relativity, the speed of light c must be same in all inertial frames. So there is a need to find such a transformation of velocity in which the speed of light will be same in all inertial systems which are actually in relative motion with respect to one another. Actually, such velocity transformation equations are found by the use of Lorentz transformations, and we will see when we will actually obtain the velocity transformation equation on the basis of Lorentz transformation equations, then the result obtained will satisfy the condition that the speed of light in free space in all inertial systems remains invariant. It is not different in different inertial frames, but it is same in all inertial frames, although the frames will be in relative motion with respect to one another. In fact, such velocity transformation equation is also known as relativistic velocity addition theorem. So, without making any late, let us now start. First of all, to obtain the relativistic velocity addition formula, or you can say the relativistic velocity transformation equations, and then later we will see its applications. So for this, as usual, we consider two inertial systems. You can see this figure. There are two inertial frames or inertial systems, S and S prime. And you are seeing here that we have assumed that the inertial frame S prime is actually moving with a uniform velocity v in positive x direction relative to the inertial frame S. And let us consider there is a particle in motion, and the observers O and O prime of frame S and S prime are actually observing the motion of that very particle. Let us consider that when the particle is at this point P, as you can see in this figure, then the observer O of the frame S measures its velocity, and let us say this velocity is in fact u, as I have mentioned here that u is the velocity of particle P measured by the observer O of frame S. So I have written here u in S, and at the same time the observer O prime of inertial frame S prime, which is actually a moving inertial frame, and it is moving with velocity v, which is constant with respect to S in x direction. This observer O prime actually measures the velocity of the same particle, and let us consider he founds that the velocity of the same particle in his frame is actually u prime. So you can see in this figure that I have mentioned here u in S and u prime in S prime. What does it mean? It means u is the velocity of our particle in motion measured from the frame S, and u prime is its velocity when it is measured from frame S prime. Now you know, to get the general result, we consider that the motion of this particle is actually in 3D space. And if the motion of the particle will be in 3D space, you know that the velocity vectors u and u prime will have actually three rectangular components, that is components along x-axis, y-axis and z-axis. Let us consider that ux, uy and uz are the components of velocity vector u in S frame, and so we can express this vector u as uxi plus uij plus uzk. You know it. And similarly, if ux, u prime x, u prime y and u prime z be the rectangular component, that is components along x-axis, y-axis and z-axis of the velocity u prime, then u prime can be expressed as the vector sum of these components in this way, that is u prime equal to u prime xi plus u prime yj plus u prime zk. You know that these I, j and k are actually unit vectors along x-axis, y-axis and z-axis. Now actually we will find the transformation equation first of all for the components of velocity, that is for u prime x, u prime y and u prime z. And for this, let us define these velocity components. You know the x component of velocity is what? This is simply the time derivative of x coordinate of the position of particle. So we define this ux as dx dt, uy as dy dt, uz as dz dt. And you know, when we actually measure the position of the same particle in frame S prime, the position are in fact x prime, y prime and z prime. And when time is measured in this frame S prime corresponding to t, that time is t prime. And relativistically, these t and t prime are not same. You have seen in the Lorentz transformation equation. So if we define the components of velocity u prime, that is u prime x, u prime y and u prime z, what will be the definition? You can see easily that u prime x is equal to dx prime by dt prime, uy prime will be dy prime by dt prime, uz prime will be dz prime by dt prime. So these are actually the basic definition for the velocity components. Now we will use to transform the velocity components from one frame to another by the use of Lorentz transformation equation. So first of all, we note here that what are Lorentz transformations. Actually in previous lecture we have studied this Lorentz transformation, its derivation and explanation in detail. So remember the results of the previous lecture regarding the Lorentz transformation, and definitely you have a knowledge that x prime is equal to gamma times x minus vt. This is first Lorentz transformation equation, and you know what is this gamma? This gamma is just a number and it is equal to 1 over root over 1 minus b square by c square. And the other Lorentz transformation equations you know are y prime equal to y, z prime equal to z and t prime equal to gamma times t minus b over c square into x. Here gamma has the same meaning. This is 1 over root over 1 minus b square by c square. Now you can see our aim is to actually relate this u prime x, u prime y and u prime z to ux, uy and uz. So first of all, we will actually find the values of these velocity components. And for finding the velocity components, we must have the small change or the differential change of x prime, y prime, z prime and t prime. What does it mean? It means we must calculate the values of dx prime, dy prime, dz prime and dt prime. And then in accordance with the definition, we will be able to define the velocity components in the two reference frames. So let us now take the differential of this equation 1. So you can say taking the differential of equation 1. When you say that we are taking the differential of equation 1, what does it mean? It means we are taking the very small change, you can say infinitesimal small change of x prime, y prime and z prime. You can see the equation and you may write dx prime, which is very small change in x prime. What will be that? You can see the equation, that will be simply dx minus v dt times gamma, because gamma is a constant. So you can see this equation here, this gamma is constant, so it is outside of the operator, and differential of x will be dx, v is again constant, so v remains same, and differential of t is dt. So dx prime is equal to gamma times dx minus v dt, and dy prime will be simply equal to dy, dz prime will be simply equal to dz. So write it here that dy prime is equal to dy and dz prime is equal to dz. Now see the equation for t prime. When we will actually find dt prime, what will be that? Gamma is again a constant, so it will be outside the operator, and the differential of this bracketed term will be what? This will be dt minus v over c square into dx. So you can write that dt prime, this equal to gamma times dt minus v over c square into dx. So actually let us say this is equation A, B, C, D, and as a whole we consider this equation as equation number 2. Now actually our aim is to find the values of u prime x, u prime y and u prime z, and for this you can see we will simply divide this dx prime by this dt prime, then we will get actually u prime x, and similarly when we will divide this dy prime by this dt prime, we will get uy prime, and in similar way we can actually find the u prime z too. So therefore we can write u prime x, it is defined as dx prime by dt prime, and for this you can see this equation A and this equation D, and let us divide the equation A 2a by 2d, and you can see that this gamma will cancel out and our result will be what? This will be simply dx minus v dt over dt minus v over c square dx. Now let us take this dt as a common factor in the denominator, and in fact we take this dt as a common factor, and also we take the dt in the numerator as a common factor. So dt is taken as a common factor. As the first term does not contain dt, so we must divide this dx by dt. So this will be dx by dt, and in second term only v will remain, and again in denominator we take this dt as a common factor, and so this will be 1 minus v over c square into dx by dt. Now this dt is 1, and you can see this dx dt is what? This is simply ux. You can see here the definition that this dx by dt is ux, and so we can write that u prime x, this is x component of velocity of the particle in the moving inertial frame S prime, and this will be what? Dx by dt will be replaced by ux, so this is ux minus v over 1 minus v over c square. Again this dx by dt is ux, So this is ux. And this is equation, let us say 3a. So we have obtained actually the transformation equation for the x component of the velocity of particle. In fact, here you can see this ux is the x component of velocity of particle in frame S, and u prime x, it is the x component of velocity of the same particle in frame S prime. And so you can see if ux is known, we can easily find what will be this u prime x by using this very result. So this is actually the first relativistic velocity transformation equation. Now to get the other equations, as I have told you, you should divide this dy prime again by this dt prime. So again you can see, you can find u prime y equal to what? This will be simply dy prime by dt prime. Here just this is change, very small change in y prime and very small change in time t prime. So this is just a division, dy prime by dt prime, this is just a division. And you can see in RHS there is dy and divided by gamma times dt minus v over c square into dx. And so again we will take this dt as a common factor in denominator. So what will be our result? Actually the dt which has been taken as a common factor, I am writing it here, dy by dt, and gamma into dt has been taken as a common factor, so here will be 1 minus v over c square into dx by dt. You can see this is dx by dt. And now you can see this dy by dt is what? This is simply uy. And this dx by dt is actually ux. So we can write this expression in this way. So let us write it here. Therefore u prime y, this will be equal to uy over gamma into 1 minus v over c square into ux. Again you know that this gamma is actually equal to 1 over root over 1 minus v square by c square. So if we substitute this value of gamma, the same equation may be written as in this way. This is uy into 1 over uy into root over 1 minus v square over c square over 1 minus v over c square into ux. Say this is equation 3b. So this is transformation equation for the y component of velocity of the particle. And as you can see from the Lorentz transformation, that actually the equation for this dy prime and this dz prime are completely identical. So if we will write the expression for u prime z, similar result as in case of y prime has been obtained will be actually obtained again. And only the difference will be what? We will simply change the subscript y by z, or not subscript, but you can say the variable. But when we will write actually velocity, then z will be at the place of subscript. So similarly, you can write without calculation the expression for u prime z. So I am writing here similarly, and you can check it yourself. Similarly, we can write that this u prime z will be equal to uz over gamma times 1 minus v over c square into ux, and we equivalently may write it as uz times root over 1 minus v square by c square over 1 minus v by c square into ux, and this is, let us say, 3c. So you can see we have obtained actually the transformation equations for the x, y and z component of velocities. So these are actually the transformation equations. Now, if our aim is to find the inverse transformation equation, you have seen how we actually find the inverse equations. For that, you can see we simply interchange the prime sign, that is, all the unprimed quantities are made primed and the primed quantities are made unprimed, and at the same time we take minus v instead of v. So when you will take minus v instead of v and primed quantities will be made unprimed and unprimed quantity will be made primed, then actually we will get the inverse transformation equation for the velocity. And so I hope you can do it yourself, but for your convenience I am just writing the inverse transformation equation for velocity components. But to follow the instruction which I have just told you, and following that instruction you can easily write the velocity transformation equations or inverse velocity transformation equations. So inverse of equations in 3. You can see the first equation is for u prime x. So at the place of this u prime x we will write ux, at the place of ux we will write u prime x, at the place of v we will write minus v, so here will be plus. Again in denominator this v will be minus v, and so that will become plus, and ux will be replaced by u prime x. So following this instruction we can write the inverse transformation ux equal to, you can see, u prime x plus v over 1 plus v over c square u prime x, and say this is 4a, and uy. Now we will write the inverse equation of this equation 3b, and you can see we will write uy instead of u prime y, and instead of this uy we will write what? We will write u prime y. And as you can see in this inside this square bracket the term is v square over c square. So when actually we will square the minus v, that will be actually plus v square. So this minus sign will remain same, it will not become plus. So we write it like this, and in denominator since v will now minus v, so this will become plus, so v over c square, and ux will become u prime x. So this is the inverse equation of this equation 3b. So this is, let us say, equation 4b. And similarly we can write the equation for u prime z. U prime z will be replaced by uz, and this will be u prime z times root over 1 minus v square by c square over 1 plus v over c square ux prime, and say this is 4c. So in these equations, all the three equations in 3, actually we have defined the relativistic velocity transformation equation, and in these three equations of 4 we have defined their inverse. One thing is very remarkable here, that you can see whenever we actually transform the velocity components, that component may be x component, y component or z component, then the term in the denominator remains same. You can see here, this is a very remarkable fact and you should remember it, that in the transformation equation for u prime x, in denominator there is 1 minus v over c square ux, and again in the transformation equation of u prime y, the same term 1 minus v by c square into ux is here too. And similarly in the transformation equation for u prime z, again you can see the same term exists in denominator. So either transformation equation is for x component or y component, but in denominator there will be always ux, never uy, never uz. It will be always ux, you can see. And similarly in the inverse transformation equation, you can see always there is u prime x. So this is a very remarkable fact and we should remember it, because students in fact generally make a mistake here, that when they write a transformation equation for y and z component of velocity, they think that there should be y and z component, but there is not y and z component, but there is actually present x component. So these are actually the general result for the velocity transformation or relativistic velocity transformation, you can say. Now actually we will think a special case of these transformation equations, or in fact the special case is in fact more important than these general results. And in this special case, what we will actually take? Now let us consider, as you have seen in the just now, we have considered that the particle is moving in 3D space, and so its velocity has three rectangular components, that is x component, y component and z component. But now let us consider that the particle is moving along the x-axis. It means the particle is in one-dimensional motion. And when the particle will move only in x direction, then what will be actually the velocity transformation equation? In fact, the result obtained in this condition is most important for the solution of numerical problems. You will see when we will actually solve the numerical problems, most of the problems are asked for the one-dimensional motion of the particle. So this is actually the most important situation. So let vector u is equal to ui. When you say u is equal to ui, what does it mean? It means the particle is moving in x direction. So this implies particle is moving in x direction. And if this vector is in x direction, you know the y and z component of this vector will be actually 0. But you can understand it, as you know, u is equal to ui, and we can write it in this way. This is plus 0j plus 0k, you can write it. And we know that this u is expressed as uxi plus uyj and plus uzk. Now you know if two vectors are equal, then definitely the corresponding components of the two vectors are equal. So you can equate this ux by u, this uy by 0, and this uz by 0. So you can see here in this condition, when the particle is moving actually in positive x direction, then only the x component of the velocity of the particle will be non-zero, and that is simply equal to velocity of the particle, and its y component is 0, its z component is also 0. You can see it. Now in this condition we will write the above velocity transformation equations. So in this condition the velocity transformation equations, velocity transformation equations become, what will be now the velocity transformation equations? For this you can see the general velocity transformation equation. Here see the equation 3a. You can write this u prime x equal to ux, and ux is now u, and so this ux will be replaced by u, and we can write u prime x is equal to u minus v over 1 minus v over c square into u. And if you write the expression for u prime y, see the previous result here, u prime y, you can see this is uy times 1 minus v square by c square over this much. But what is this uy now? You can see here that this uy is actually equal to 0, so the whole result will be 0. So uy prime will be 0. Again, you can see that this u prime z will be also 0. You can see here in the transformation equation defined in this equation 3c, you can see that u prime z is equal to uz into root over this much. But this uz is now 0 in accordance with our consideration, and so this is also 0. So what you are seeing here, you can see that only the x component of the velocity of our particle in frame S prime is non-zero, and the rest two components are 0. So there is no need to write a subscript x here, and this is why we will write this u prime x simply as u prime, not u prime x, because u prime y and u prime y and u prime z have been become 0. So we write simply this equation u prime equal to u minus v over 1 minus v over c square into u. As I have told you, this is a special result is more important than the general result, because most of the applications, most of the problems are asked in your examination based on this result. So I here also change the equation number. This is a very important equation, so we write it equation number A. And now you can easily write again the inverse of this equation. You know the technique or the trick to write the inverse. For writing the inverse, what you do actually? We simply replace this primed quantities by unprimed quantities and unprimed quantities by primed quantities, and v is replaced by minus v. So inverse of A, inverse of this velocity transformation equation A will be what? This will be u equal to u prime plus v, because v is now minus, so minus minus will be plus, and in denominator again you can see this v is minus, so here will be plus v over c square into u prime. So this is actually the inverse transformation equation for the velocity of the particle in one dimensional motion, that is for a particle which is moving actually in positive x direction. So you can see from these equations A and B, if you know the velocity of the particle with respect to the inertial frame S, which is actually u, then you can find its velocity u prime, which is the velocity of the same particle with respect to the frame S prime. So this is called actually the velocity transformation equation. And as this equation has been obtained by the use of Lorentz transformation, and so it is known as relativistic velocity transformation equation. And this equation B is its inverse. So this is also a relativistic velocity transformation equation. And you can see, in accordance with equation B, if we know the velocity of a particle with respect to the moving inertial frame S prime, which is u prime, then this equation B actually enables us to find the velocity of the same particle with respect to the stationary inertial frame S, and that velocity is u. So if we know u prime, we can find u, and if we know u, we can find u prime. So these are actually the velocity transformation equations. Actually, these two results are also known as relativistic velocity addition theorem. Now you can see, as I have told you earlier, that the Galilean velocity transformation equation is not consistent regarding the fact that the velocity of light, or you can say the magnitude of velocity of light, which is called speed of light c, is not same in different inertial frame in accordance with the Galilean velocity transformation equation. But now you can see this relativistic velocity transformation equation will say that speed of light in different inertial frame will be not different, but that will be same. We can check it, and for this let us see how we can check that the speed of light in free space c is same in frame S and in frame S prime. It means if instead of our particle, now we consider the light, and you know the light quanta is actually known as a photon, or in fact when you say light quanta, it means particle of light. So a photon actually moves with a velocity equal to c in free space. And you know, you can see in later lecture that a particle actually whose rest mass is 0, such a particle can move with a velocity equal to velocity of light c. So actually the rest mass of our photon, which is a light quanta, light particle, is actually 0, and so this photon is able to move with a speed c. So now instead of any ordinary particle, let us consider our particle, which you have considered that P is a particle in motion. Now consider this particle is not any particle, but this is actually a photon. And if it is a photon, then its velocity, let us consider in frame S, is equal to c. So let our particle is light quanta. Light quanta, quanta means particle, that is photon. And its velocity in free space relative to frame S. relative to frame S is c. When you say that velocity of this photon relative to frame S is c, what are you saying actually? In fact, it means we are considering that u is equal to c, because we have considered that u is the velocity of our particle with respect to the inertial frame S. Now our particle is photon, and photon's velocity is actually equal to c, which is velocity of light. And as I have told you, it is possible for photon that it may move with a velocity c because its rest mass is 0. Because special relativity actually says that a particle having 0 rest mass can move with a velocity of c. No massive particle can ever attain a velocity c, but a massless particle may have a velocity equal to c. So actually the photon's velocity is c, but with respect to what frame? With respect to frame S. We have actually considered it, that the velocity of our photon is c with respect to frame S. And as I have assumed that velocity of our particle is u with respect to S, so in accordance with our consideration, now we will actually write c instead of u. And now let us find velocity of the same photon in another inertial frame S prime. In accordance with Galilean velocity transformation, the velocity of photon in another inertial frame will be different. But you can see here that in accordance with our relativistic velocity transformation equation, you will find that velocity of photon in frame S prime will be again equal to c. But how? You can see here. So velocity of the same photon relative to S prime. I am again repeating the result here for your convenience. You will know that if we know the velocity of a particle with respect to frame S, which is u, then we can actually find its velocity with respect to S prime by using this transformation equation. You have just studied that u prime is equal to u minus v over 1 minus v over c square into u. But see here, our assumption is what? Our assumption is that the velocity of our particle, which is now photon, u, is now equal to c. So let us replace this u by c. So our result will be c minus v over 1 minus v over c square, not c square into c. And so this will be c minus v. Here 1c will be actually cancel out, and in denominator that term is 1 minus v over c. Take the LCM and you can see this c will be in the numerator, c minus v over c minus v, and this will cancel out, and you can see our result is u prime equal to c. This is just a surprising result. You can see that when we have considered that the particle photon is moving with velocity c in frame S, then it is found that its velocity in frame S prime is again c, not different. But according to Galilean velocity transformation equation, this u prime is not equal to c. But this is in fact in accordance with our second postulate of special relativity. We have in fact studied that in accordance with the second postulate of special relativity, speed of light in free space c is an invariant. It does not depend on the state of motion of the source, of the observer, and the reference frame. So it is verified that velocity of light in free space is same in all inertial frames. So it is treated as an absolute constant, or you can say it is a relativistic invariant. So C is what? C is a relativistic invariant. In fact, let us say this is just point number 1. It means in this point number 1 we have assumed that the velocity of photon in frame S is C, and then we have obtained that its velocity in frame S prime is equal to C, again C. Now just we consider that velocity of photon or light is C with respect to the moving frame, and then we will actually find its velocity in frame S. You will again find that this velocity will be again C. But how? You can see here. Now let U prime equal to C. When you say U prime equal to C, it means you are considering that the velocity of photon with respect to frame S prime is equal to C. And if we have considered that U prime is equal to C, then what will be U? You can see from the transformation equation. You know U equal to what? This is U prime plus V over 1 plus V over C square into U prime. But our assumption is what? Our assumption is that U prime is equal to C. So let us substitute C instead of this U prime. So this is C plus V over 1 plus V over C square into C. Again this 1C will cancel out and you can simplify it. This will be C times C plus V over C plus V. And so this will cancel out and you find that U is equal to C. So you can see, if we assume that velocity of light with respect to frame S prime is C in free space, then it is found from this relativistic velocity transformation equation that its velocity is in fact again C with respect to frame S. So what we conclude from here? Actually, you can see that the velocity of light C is a relativistic invariant. Its value is not different in different inertial frames. Actually, this is the second postulate of spatial relativity. So, using the Lorentz transformation equation, it is possible to show that the velocity of light in free space remains same in all inertial frames. Now, I have told you earlier that whenever we actually impose the condition of classical limit on any relativistic formula or any relativistic result, that result actually transforms into its equivalent classical result. So now let us impose the condition of classical limit on the relativistic velocity transformation equations, and you will see when we will actually impose the classical limit condition on relativistic velocity transformation equation, those equations will be actually converted into the equivalent classical velocity transformation equation, which are actually known as Galilean velocity transformation equation. So now let us see what are the classical limit of these results. Classical limit. You know, you have actually studied several times. What is classical limit? The classical limit is what? This is V is much smaller than C. In other words, you say V over C is much smaller than 1. In fact, this condition is known as classical limit. You know it. We have in fact used this idea several times. This is known as classical limit. Now, if we impose this condition on the relativistic velocity transformation equation, you can see in comparison to C, the quantity V over C square, the quantity v square over c square, all will be actually neglected, and we can take their value 0. So you can see that when v and u are very small, so when v and u are small, when you say small, it means very small, then as compared to c, the term like vu over c square and v square by c square may be neglected, and so you can see the velocity transformation equations which we have obtained here. You can see these equations here. Actually this v over c square into ux will be neglected in comparison to 1, and in this equation number 3b, we will actually neglect this v square over c square in comparison to 1. Again in denominator we will neglect this v by c square ux in comparison to 1. And similarly in case 3c will be also the same result. And so after neglecting those terms, what will be actually the velocity transformation equations? So you can see these transformation equations will be u prime x equal to ux minus v, and u prime y, this will be equal to uy, and u prime z, this will be equal to uz. And you can recognize these equations as you have studied in the previous lectures, the Galilean velocity transformation equation. And if you remember, you can say that these are nothing but simply the Galilean velocity transformation equations. So these are Galilean velocity transformation equations. And so you can see when we actually impose this classical limit condition that v over c is much smaller than 1, then our relativistic velocity transformation equations actually change into their classical equivalent, which are actually Galilean velocity transformation equation. So this fact is also in fact verified here, and this is all about the relativistic velocity addition theorem, or you can say the relativistic velocity transformations.